In this video, we're going to continue with the hydrogen gas and the water shift question. So we've answered question 1 and 2, and question 3 says the equilibrium constant for the water gas shift reaction at 500 degrees Celsius is 7.83. What is the equilibrium concentration of all the reactants and products if a starting concentration of 2.0 mole per liter of both carbon monoxide and water vapor are reacted? And so I've built an ICE table. It says that the Kc, and this Kc expression is here, the Kc is 7.63, I believe it says, or 7.83. So 7.83 will equal the concentration of these chemicals at equilibrium. This is 2.00 mole per liter, and this is 2.00 mole per liter. And that's the information that's given to us. Well, I need to know the equilibrium values to use Kc. So these are starting at 0 because it was an empty container that they've added those to. So if we made X CO2, we would also get X H2, and we're using up X of both of the reactants. So this is 2.00 minus X, and this is 2.00 minus X. And so I can use these values in this. So I'm going to get 2.00 minus X times 2.00 minus X. Those are the reactants, so they go in the denominator. And I get X times X for the reactants. So I get 7.83 equals X squared over 2.00 minus X squared. So if I take the square root of all of these things, I will be able to then work back to X. So the square root of 7.83 is 2.80. And then the square root of X squared is X. And the square root of this is going to be 2.00 minus X. So I'm going to multiply these. So 2.80 times 2 is 5.60 minus 2.80x equals x. So I'm going to group my x's. So I'm going to have 5.60, and I'm going to add 2.80x to both sides. That's going to get rid of this. So I get 3.80x. So x is going to equal 5.60 divided by 3.80. So I get x is equal to 1.47. And so this number is 1.47. This is 1.47. This is going to be 2.0. 2 minus 1.47. So that's 0.53. And this is 0.53. So we've got the equilibrium concentrations of all of the chemicals. So that was the question 3 that we've answered. And then question 4 says, is the water-gas shift reaction endothermic or exothermic? Based on the calculated equilibrium constants in question 2 and the given constant in question 3. Well, this is a little bit more of this is a pretty deep question. So we've got carbon monoxide gas and we've got water vapor in equilibrium with hydrogen gas and carbon dioxide gas. So let's think about this a little bit logically. If it is exothermic, so we had energy as a product. If it is exothermic, then heating decreases Kc. Right? Because it's going to shift to the reactants to use up the extra energy from heating. So it would decrease the Kc, and that means that it's exothermic. If it is exothermic and we cool it, Kc should go up. So if it's exothermic, then cooling will increase the Kc, because I cool it and it drags the energy this way. But let's say that it's endothermic. So the energy is a reactant. If endothermic, then heating would drive the energy or drive the reaction this way to use up the energy. Then Kc would increase. If it's endothermic, then cooling will make the Kc decrease. So now let's take a look at our results. The Kc at 500 degrees Celsius was 7.83, and the Kc at 150 degrees was 90.6. So at 150 degrees Celsius, it was 90.6. So we can see that as we have heated it, so we're heating it up, so if it's exothermic and heating, the Kc decreases. Well, that's what's happened. At the lower temperature, it has a Kc that is bigger than at the higher temperature. So if exothermic, then heating decreases the Kc, right? And we could look at it the other way. We had the Kc when it's cool to hot. We've heated it, the Kc goes down. So as we heat it, the Kc goes down. As we cool it, the Kc increases. And so it's a lot of thinking to go along with that one, but a little organization will get us there. So question 5 says, industrial applications of the water-gas reaction are carried out at high temperatures. Does Le Chatelier's principle support this choice? What other reasons might you do this? So they do this reaction at high temperature, but the Kc is actually kind of low, so we're going to get less products. If we are getting less products, that's not industrially favorable. Why would we want to get less products if we're doing that? But even though the Kc doesn't support this, right, because we've said that it's exothermic, you might heat it up because it increases the reaction rate. So it increases the forward and the backwards reaction rates enough to overcome the not favorable Kc. So you're just speeding up the reaction so much, both going forward and back, that you actually get more products. The last question says, what are 2 ways to increase the yield of the water-gas shift reaction? Well, if I want to get more products, I could add more carbon monoxide. I could add more water, kind of the same idea. If I could remove the hydrogen or the carbon dioxide, it'll shift the reaction to the products. And then, as we've already said, if you cool it down, that'll increase the percent yield. So those are all options. So hopefully that makes sense. Take care.